Alright, another draft physics video presentation and such. Brought to you by something or other. Oh, comments first, and then on to Biezen and photons. So this is mostly photons, I think, in the comments, which is good. But anyway. Hey man, can you please offer your thoughts on these high-speed photon photos relative to your model? I've already commented on these high-speed photographs. So it's like the coal. It's not really a photograph. So these pictures of photons moving aren't really a picture of a photon moving. Because photons are all kind of alike, what they do is they basically take zillions of pictures of different photons doing the same thing and then put them together and say that's the average function of a photon. So it's not seeing the same photons moving. Second, obviously you're not seeing the photons moving, you're seeing the photons hitting little particles and being reflected to the camera. So you're not seeing a photon where it's going, you're seeing a photon that has been deflected into the camera. And so it's just a bunch of images of where the photon gets deflected to a camera. And it's a bunch of different photons that are creating the image. So they walk through the same thing over and over and over again, and it's a different thing going through each time, and they're just giving you an average picture. So it's really not what they claim it to be. It's a synthetic photo. And I don't know if it has any value at all anyway. I don't think it illustrates anything that is surprising. Photons travel in a direction, and they hit objects in their way and reflect. You can't take a picture of a photon actually moving. Can't do it. It's impossible. And that's what they ought to just say. It's impossible. All right. How would it image through single double slit? Well, first off, the whole point of this single and the double slit is that those photons are broken. And again, all you could see is ones that didn't do anything, didn't get to the target. You can only see the photons that you take out of the experiment, the ones that come out of the experiment. So you're not going to see anything that could possibly be relevant, because first the photons are broken and have to be recombined to be even seen as a photon. And so if you deflect a broken photon, it's the same as deflecting nothing. You won't see it. So it'll give you a picture of nothing. If you tried to do it, you wouldn't see anything. Forgive me if it's a dumb question. Well, it's not dumb once you start realizing that you can't, that these photon things are composite things. It's energy, quantas of energy moving in a direction, and the different bits are doing different things, and then you're seeing a composite of it, even in our world. It's not the real photon. It's different elements coming from different locations, and it's put together in one location. And so you say that's a something, even though it didn't really come from exactly where you think it came from. The light you're seeing in the bars on the pattern is a composite of two different photons being combined in a location, saying this is where we came. This is so you can't follow their path through history, because their path is made of two paths, if you get me. You can't reverse it and have the expectation that you reverse it into a simpler thing. You're going to reverse it into a more complex thing. All right. How would it... dumb question. Don't be a soap nasty, whatever that is. I just an intrigued jobbing electrician. Dig your hypothesis. So he leaves a link, but it's a link to, again, it's just it's not interesting. That's my impression. Uninteresting. Completely synthetic. Not really a photograph. Not really, even if it was a photograph, it's not a photograph of the photon, right? Again, the only photons we can see are ones that didn't do what they were doing. They bounced off something to go to us to tell us there was a photon there. But the photon didn't do what it was supposed to be doing, quite obviously. So obviously it's not the same photon you're watching. You're not watching one photon go through its existence. You're watching a bunch of photons that actually never accomplished the task of getting from point A to point B. They never did that. Instead, every single one of them got deflected to the camera. Clearly not a photograph. All right. Hey, DraftScience, hope you see this. Well, I have a better chance of seeing it if you don't put a bunch of empty space in it. From what I've gathered in your theory, so this is always dangerous, right? Because no matter how explicit I am, no matter how much I make such an effort to say things as clearly and directly as possible, you people can't paraphrase me worth shit. I found flaws in something you imagined wrongly. I want to point out. Okay, here we go again. The attractive electric force has the same origin as the gravitational force. Where did I say that? I'm saying charge is the fundamental force. The only one that exists is the fact that electrons and protons exist, and there's a force, two forces, that are complementary to that bisected universe. There's a plus force and a minus force, or an electron force and a proton force, a red force, a black force, a north force, a south force, however you want to describe it. But there's two forces of elemental different bits, two kinds of arrows. Yeah, I can draw that. There's this color, and there's this color. Okay, and there's electron, blue thing. Oops! Now I dropped my yellow chalk. All right, I'll draw it as a yellow thing, as a white thing, and a white thing. That's it. That's all there is in the universe. So there's a ton of this stuff going in all directions, and there's these protons and electrons. Okay, and that's all there is. That's what I've said. And I've said when you mix these things up, that is the blue thing and the white thing, and you mix them up in the universe in all kinds of different places, and you don't have them in order. Okay, white, blue, white. See, this is magnetism. Okay, when you have them in nice clean order, then they magnify their effect, and what they create is a universe that is doing a lot of bluing this way, and a thing that's doing a lot of whiting this way. All right, and that's a magnet. And when they're individual charges, they directly interact with these two different forces exactly the opposite way. The white force reflects, and the blue force does this perpendicular thing. So you have two opposite reactions by the two opposite forces, and clearly that's the only thing happening in the elemental universe. Gravity, okay, is these elemental bits are the ones interacting with the force, but the point is when you mix them all up, that is, you don't have these poles in the right order, then this is yin and this ends up being yang, and you end up with the same amount of yin as you have yang, and so the charge aspect is eliminated, and all you have is the proximity argument. So when the two things are close to each other, there's obviously forces absorbed, and there's less force in here, but it's not charge. They're not doing a charge phenomenon because the charges are all mixed. So the attraction and repulsion between the charges is negated because they're plussing and minusing in random directions that neutralize any electron or proton force. So I've clearly stated the moon isn't positively charged, the earth isn't positively charged, the earth isn't negatively charged, and the sun's positively charged, and they're attracting. None of that stuff is happening. There's no electric universe in that sense. There's no charge phenomenon in the gravity scale. Big objects aren't charged, and if they are charged, they're not charged in any significant amount. And if they're magnetic, they're not magnetic in any significant amount. So it's not a player in their interaction with each other. So your premise is wrong. Okay, the attractive force has the same origin. It's not the same origin because the Earth isn't charged, the Sun isn't charged, they're not the same as electrons and protons. The force of attraction, again, is if I neutralize the 2 plus 2 thing, if I took away the identity, the difference between electrons and protons, the argument would be if they reacted the same way to the force, the same thing would happen. The analogy is with BBs. I put a bunch of BBs in a box and give them all motion. Okay, no color necessary, no distinction between charges necessary. And I put 2 big objects in there, the BBs, just by random interactions, will end up pushing the 2 things together. Because there will always be more BBs hitting it from the side that they're not shadowing. So clearly the gravity argument is a shadow argument. It's not made out of charge. But I'm just saying, to be honest, to be truthful, the only interactions that are moving anything are electrons and protons, and they are charges. But when you mix them, that you negate any meaning to that. The fact is, though, they will push each other along. I don't know how else to say it. If you move the proton, the electrons go with it. All right. How do we explain the difference in their strength? So again, there's no difference in strength that needs to be explained. The Earth isn't charged. It's not an electron. It's not a big giant electron. And you say, well, how much charge does the big giant electron have? It's not the same phenomenon. It's not the same thing. Okay, mass isn't charge. And again, it's obviously I'm pointing out how any charge effect is negated if I have a charge pointing this way, a dipole this way, and a dipole this way, and I make a dipole in all the directions that are opposite each other, that there'll be no effect. If I have a magnet going this way, north-south, and I put another magnet south-north, I've negated the meaning of the magnet. All right. Additionally, how do you interpret the charge and mass? How do you interpret charge and mass? From the electron's perspective, the only thing that matters is its charge. From the proton's perspective, that's all that matters is its charge. Its mass isn't terribly relevant. Okay, it's not a meaningful player in any sense other than its reactivity. How much can it react to the force that exists? And measuring its charge is measuring how much it reacts. So in a sense, for our utility, charge is mass. Charge is the ability to be affected, to create an effect, to repel, to have stuff bounce off you, or to have stuff deflect through you. That's the boat. The boat is just whatever it has in it, the forces, the people rowing the boat. And again, the exchanges that take place. So it just basically, charge is just saying how big is your boat. That's it. That's mass. How much force do you hold? How many rowers can you exchange? I don't know how else to say it, but that'll have to do. Okay. How do we translate Coulomb's law and mentions 2 charges to your argument theory that's based on the shadow of force bits? I think that's what it says. It says forcets. I don't know what that is. It's called what I call your force bits. Well, forcets isn't very useful, in my opinion. But whatever, force bit, that isn't too much to ask for people, that one particle cast on another. Let's see how to say this a clearer way. I'm just saying you have to just understand that all the charge is negated if you mix a bunch of electrons and protons together. And this, you just mix a whole bunch of them together and randomly. You don't have any charge. There's no charge on the object. But the truth is that it's still consuming force in the sense that the little bits will move. And if the little bits move, they absorb something that was going somewhere. It's not going to get where it was going. That's gravity. So even when they're mixed up, they're going to create effects. It won't be in a charge effect, though. It's not the same effect. Like I said, you're saying that somehow the gravity has got to be the same as charge, and that somehow the Earth is charged positive and the Sun is charged negative, and that they should have this incredibly strong attraction to each other. Well, they're not charged positive and negative. They're not, but I'm just saying they are obviously made of charges. Obviously, I'm stating they're made of charges. Charge is ultimately the cause of all motion. But when you mix the charges, it has no polarity anymore. It doesn't mean anything anymore. And all you have is its effect to absorb motion. And the bits are moving. The reason why the Earth is creating gravity is because bits inside the Earth are moving. And to move, they have to make exchanges. Forces have to jump in their boats. Okay. All right, I believe that gravity has a different origin. Oh, I don't know. Did I care what you believe? Oh, no, I don't think I did. And found an interesting alternative explanation that explains time dilation, etc. Well, fine, but I'm still working on it. We'll update y'all, though. Well, thank you for the update. I don't think you're going to find an explanation that works better than this one. This one explains charge, magnetism, gravity, the nuclear forces, all of it is explained. It's done. It's complete. And there's only two forces and two matter bits. And it's all done. All the physics is explained. All the interactions are explained. It doesn't leave anything out. So I can wish you good luck, but I don't think there's an alternative. All of the gravity moves at the speed of light. That's giving you a clear explanation that it's exactly the same force that electricity and magnetism are. They're all moving the same speed. And photons are moving the same speed. It's all moving the same speed. It has to be one force. So if your alternative explanation doesn't have one force, that is at least one force in the idea of the basic thing. Like I said, I'm saying there's two forces, but I'm just saying there's really one force and it just comes in two colors. So it's one model of car and it comes in blue and red. And the color really matters to protons and electrons. All right. I really can't. I don't know how to make it any simpler. At this moment, I don't know. I obviously have to do that, but I can't do it off the top of my head, I guess. I have to construct the simpler argument. I don't know. Like I said, I think I have constructed it. Anyway, would be hilarious if you bought one of Ken's leather bags that he makes and show it off on your channel, LOL. I don't know why that would be hilarious. No idea. But whatever, yeah, I'm not into whatever style and leather and all, whatever. Fuck that. Just give me cheap. So, hell with that. Alright. Hope I'm not being rude, but have you thought about email some information, i.e. diagrams, etc., maybe a short video to some of the recognized theoretical physicists? Yes, I have, and it's been of no... I have gotten nowhere. So I've offered them money, plainly. I've overtly asked them for a price list of how much I'd have to pay them to have an hour of their time. And I've gotten nothing in response. I mean, Professor Lewin did respond, and his catch was that he's working on his own master theory, and he doesn't want to compromise his intellectual property or whatever, some kind of crap like that. But yeah, the rest of them, no response. I mean, you can't even offer them money, and they still won't respond to you. Not very polite business practice, I'd say. But anyway, that might review some of your ideas, and they might get some more mainstream attention. Yes, that is exactly the plan. But the point is they don't want to be shown up. So unless they can be making fun of a flat earther or something, they'd love to be paid to do that. But they really don't want somebody who's going to challenge how well evidenced their garbage physics is, and how point out how poorly evidenced it is, and how they just made this whole theory up. It's just a Hansel and Gretel story. It really doesn't have much relevance to the truth. There's no gingerbread. There's no witch. those things don't exist. Anyway, Michio must have been in your position before he proposed string theory. Well, that's just bizarre that, he has stolen it, frankly. I mean, he didn't propose it. He might have helped popularize it, but he didn't propose it. He didn't invent string theory. And it became popular. Yes, when it's just nonsense. I mean, it's just silly. Little vibrating string is another non-answer. The magical vibrating string did it with its magical vibrating powers. I mean, it's like just saying the universe is based on eternal jellyfish. Like there's a jellyfish at the core of the universe going blah, 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 But you don't have to explain how the jellyfish works. These are all just fake replacements for the right answer. All right, so I guess that's enough. So on to this video, which unfortunately is mostly mathematics, and it doesn't really say anything more than he said in the last video, but we'll try to make something out of it. Where's my eraser? May need this. So, I should pause while I'm erasing. There's no real fun in it for you, right? Racing isn't very exciting. So anyway, play the video, Gary.
Welcome to Electron and in our quest to figure out what a photon is. Now we're going to take a look at a photon and its momentum. Yes, we do know that a photon has momentum, even though it doesn't have any.
Even though it doesn't have any
bright
mass.
Brain full of activity. That's a healthy
annoying.
18-year-old brain. Mine is the other one.
It doesn't have any mass. So going back to the original.
So it doesn't have any mass, and so going back to the same formula you used before, in this argument of momentum. So let me try to preface this. So the simple idea is that there's something called energy conservation, but the problem with their theory is they never define the energy as being in the form of these little bits of quanta. Okay, so whether, again, I'm not, if you want to keep your stupid little wave theory, the idea is that the wave is quantized. It has clumps to it. Okay, bits that are causing the action, the perturbation, the high pressure, low pressure, however you want to think about it. And it's sort of important. So their argument is that all I have to do to make energy, and I would argue to some extent this is true, but it needs to be qualified, is that all I have to do is change these four things and just make them four things closer to each other, and I've created more energy. Now, my argument is that no, that's only more energy to something that can sense it as more energy. That is something that can be tipped over. So if you throw a medicine ball at me, a heavy ball, and you throw it at me, and throw one at me, and then I'm able to catch it and then bounce back, right? You can throw four of them at me and I'll still be standing up. But if you throw them fast enough where I caught it but I don't get to stand back up again, and you hit me again with another medicine ball, and then you hit me with another medicine ball, you knock me over. All right, and so this is the key to what's defined as energy is, well, did you knock the guy over? Now, it's not about the force, it's about whether you knocked him over. The problem with their theory is the electron is so tiny, I can't even make it visible, it's so small relative to the size of the polarization, okay, of this way. You can see the cartoon. What was I going to say? Yeah, so this thing can't be interacting. The electron is a tiny thing, tiny. So this thing can't be reacting with one electron, the whole length. Realistically, you can't think that this dot, this dot, this dot, and this dot, right, they're spread in space, all hit the same little infinitesimally small particle. So obviously this has to be something atoms interpret, and they end up doing this tipping thing and blah, blah, blah. And all this is a little more complicated than this thing interacting with another thing, in like as if all four of these bits are now going to hit something called an electron. It's not going to happen that way. They're going to be interpreted as little bits, and the atoms are going to react in some collective way that will in the end create a single action. Okay, but there won't be any the electrons that are individually getting hit are always going to be hit with exactly the same amount of energy. Boom, a bit. Boom, a bit. Okay, so there's no, so the problem I'm describing is that by making this frequency closer, because they've said this equals energy, right? Closeness means you tip things over. Well, the point is that once you've tipped it over, once you're fast enough to tip it over, any extra energy is totally irrelevant. Because you already knocked it over. There's only knocking it over. There's nothing else. You can't add more than just knocking it over. It's useless to even try. And then, so by their theory, they can just make this distance infinitely close. So they can come up with some infinite way. They can put an infinity in here. All right? As distance between these objects and make this infinitely energetic. They can give it infinite energy by just making this frequency smaller and smaller and smaller, the distance, the wavelength. And that gives them infinite energy. And so it's just like bent space, where you have the infinite gravity well, okay, that goes down forever and ever and ever. Same problem. There's no real physics to that. They've never proven there's an infinite supply of water, so to speak, to fall down their well, and there's no evidence that there's any 4 little bits of quanta hitting 4 electrons in different places that somehow they can turn that into an infinite amount of energy. So it's all theoretically kind of nonsensical. All right, what else do I want to say? All right, so let's dissect it a little bit more. Need more wettitude. Have to do. It's drawing green, maybe. Yeah, color changes are fun. Okay, so what's going to be pointed out here is that this idea of a photon is interacting with an electron. So the photon has energy because it's moving very fast. And so they're saying that this photon is going to bounce off of this electron in some new direction. And they can't change its velocity. So the only thing they can do is change this theoretical frequency. But again, the interaction is just with this bit. This is the quanta. It's just one quanta hitting one electron. And the energy is always the same for each individual quanta bit. The time factor doesn't mean anything in this context. How fast you hit it doesn't mean anything. How often you hit it doesn't mean anything. So all you're talking about is this quanta interacting, and it's going to change its angle. Well, this can't possibly lose momentum. This quanta of a photon, this piece of a photon can't possibly lose momentum. So what you really have to do is essentially give the momentum to this. So this can't really reflect and then this move, because you can't change the speed. You can't take any momentum out of the photon. So if I made it reflect, then this couldn't possibly move because I've already used up all the energy. The reflection is leaving with exactly the same momentum as this came in. You can't change its momentum. You can't change the mass of this thing, and you can't change its speed. So you can't possibly change its momentum, so it couldn't possibly make this also move. So the only way the action can really happen, okay, is that the little photony thing has to put its energy inside of this. And if you did it by my rules, it's kind of funny that it comes out to this 2 number. They multiply by anywhere from 0 to 2. So they call a perfect reflection a 2, right? And that's in the equation. Now, where does that 2 come from? Well, it comes from my explanation, where if this little bit of energy goes inside of this thing, so let's draw it bigger, just so it's more illustratable. All right, so we're saying that there's already energy inside of the electron, and it makes an exchange. So that is, it hits head on with a piece going the opposite direction. So that piece goes away. That rower jumps out of the boat, goes that way. He's irrelevant. This piece goes inside of the boat. So the boat lost something going this way, right? That got erased, and it gained a rower going this way. So that's a 2x increase in its momentum, in the sense that it lost something going that way, and it gained something going the opposite way, which is 2x. All right, and then this electron, now later, okay, after it moves some distance, now it can stop. Okay, it can do exactly the opposite. It can give back the world this. All right, and the thing it's going to get is this back, and it's going to have a 2x change in exactly the opposite direction. So you give it back again, and that's the scatter. So the scatter can be in this direction, or it can be in this direction. But obviously, if it's in the opposite direction, that's the 2x perfect reflection. That is, that's when you put this guy in the boat, and you let this guy leaves the boat. That's the 2x. If it's at some other angle, then it's less than that 2x proportionally. And exactly the opposite direction would be fundamentally impossible. You can't let this energy hit that energy. So you can never make that replacement. Something going the speed of light can't hit something going the speed of light in the same direction. So anyway, so that's the 0. Because it never happens. Okay. So what else is it? So that's the way to understand the scatter formula. And so just look for the 2 part. The 2 doesn't have anything to do with their theory. The 2 has to do with this way of understanding it. So, put simply, the photon hits the electron moves, and then the photon is re-released when this thing stops. So when this thing loses that momentum, or drags to a halt, the photon is re-released. The bit of energy here is now leaving back here, and this is the time delay. This is why light is slower in glass, is because this moves much slower, all right, than the speed of light, this electron. It goes 2x faster than it was going, but it's still much slower than the speed of light. But that's real conservation. There's no conservation in the stuff they do. They end up with way too much energy, frankly. I mean, kind of obviously.
Original equation of relativity, where the total energy of a particle is equal to its rest mass energy plus its momentum times the speed of light quantity squared. And of course, in the case of a photon, it does not have any mass, so that portion will go to 0. And if we then take the square root of both sides, we can see that the energy of a photon is equal to the momentum times the speed of light, which means that the momentum of a photon must be equal to its energy divided by the speed of light. And since the energy of a photon is equal to Planck's constant times the frequency, we can say that hf divided by the speed of light is equal to the momentum of the...
Right. So this is the typical deriving of equations where you do replacements, and this is completely a bogus replacement. Okay, you've pretended that you can make momentum without mass, which is nonsense, and then you've decided that you're going to make this frequency thing the relevant factor when it's only relevant to one circumstance, knocking me over. Exchanging energy just requires you to throw the medicine ball. That's real energy. It's a real event that happens. The event of me tipping over is a different event. And that's the one they're paying attention to. That's the one they say is energy. But there's energy in the whole system.
Photon. Since we typically like to work in terms of wavelength, especially when we're going to include the Compton scattering, we can also say that the speed of light c is equal to the frequency times the wavelength, which means that the frequency can be written as the speed of light divided by the wavelength. So replacing that here, we can say this is equal to h times c over c times lambda. So instead of f, we can write c over lambda. The c's cancel out. So finally, we can say that the momentum of a photon is equal to the Planck's constant divided by the wavelength of the photon.
Which is the same thing again. So the wavelength, this is really just the reciprocal of the frequency. So you've just changed their positions. You put the reciprocal number in the denominator and put the other one in the numerator. So you've done exactly the same thing. So yeah, it's quite meaningless. And again, you have to believe that it matters how fast I throw the medicine ball is the only thing that matters. So how fast I shoot the bullets is all that matters. The bullets don't matter. The bullets don't have any energy. And it's kind of mocking quantum mechanics to think that I make more quantum by putting them closer together. That's essentially what they're doing. They're saying there's more quanta of energy because I made them closer together. And there isn't explicitly. There is if I'm shooting rays exactly 1 second worth of ray and it's a continuous ray. Well, quite obviously, that would take an insane number of billions of little quanta would have to be in one ray versus the ray that only has 6 in it. I mean, obviously the one that has billions is going to have more energy. But there's no source for those rays. There's nothing that produces those kind of rays. The rays are just usually have, 20 or 30 quanta in them. And you can't extend it. You can't make the ray longer by making the frequency smaller. You're not making more quanta, and they think they are.
So when a photon then, for example, hits a particle, of course, when it hits a particle, photons don't hit really, they just interact between the changing electric field that they set up and the charge of the particle that they're coming in contact with, and again,
right. So they just mush right over this whole concept of the interaction. So they're not taking any account for how this physically could possibly happen. They're just giving you this imaginary notion that this big giant thing is doing this through space and it interacts with one electron here and doesn't bother any of these other electrons anywhere else in the space. It just bothers this one and vibrates him by some magical theory that can't possibly make any sense. And he just says that's the premise, though. I'm supposed to take that nonsensical description of reality, and I'm supposed to just give him the benefit of the doubt. Just believe in gingerbread, believe in witches, and now my silly story will make sense.
Contact is a kind of a loose term. We can see that there's then a change in momentum, and that change in momentum, or the momentum imparted in the particle, will be equal to h over lambda in the case of a photon. Now, it could be that there's only a partial change in the momentum so that the photon comes back with a reduced momentum, and the difference in momentum is then being imparted on the particle. So we're going to...
So again, this idea that they made the frequency smaller, and then they're saying there's an interaction, and now the electron moves much faster. Now, it's true, the electron will have velocity dependent on its tension. How just as me with the medicine ball, if you throw the medicine ball and I'm standing on ice, well, then all of the impact, I'm going to move because I don't have anything grounding me. I don't have any tension with the ground to allow me to spring back. So, but there's not enough quanta in the ray to produce the energy they're claiming exists, and they're only making it exist because they're saying for any amount of time I can fill in more quanta. So if I need to make the ray infinitely long, I can make it, infinitely dense, I can keep it the same length. So I can just add all these extra bits. So when I go from an 8 bits, 8 long, and I shrink it by making the little bits closer to each other, I can just fill in that extra time with a whole bunch of quanta. And that doesn't happen. No chance.
Try and figure that out when we interact between a photon. We look at the interaction between a photon and an electron, like in Compton scattering. So we're going to take the example, to make it a little bit easier to work with, that the photon is inbound, hits the electron, and then ricochets off the electron, coming back in the opposite direction with a angle of 180 degrees.
So we did this before, so it's just basically the same thing. It's going to be all mathematics. But here's the formula. Okay, change. This is the wavelength 1, wavelength 2. So this is the formula for measuring how much of a change there is in the frequency of the light coming back, and they're calling that energy, all right, in a sense. But here's the part that's important, is this cosine here, 1 minus the cosine of theta, that is this angle. And so this angle is 180 degrees, and that makes it the number 2. So this is essentially saying multiply this times 2. And that's the same thing as saying basically what I'm saying, which is you're going to give back to the universe this, and the electron is going to take in this. So it's going to lose something going that way. It's going to gain something going this way, which is a doubling of its momentum in this direction. But it still has to spread that momentum over its entire mass. It doesn't get to go the speed of light. You can't, flick a bowling ball with your fingers, and the bowling ball moves as fast as your finger was moving. Okay, the energy you put in has to be spread over the entire mass. So the electron's going to leave, but it can't leave at the same speed, quote unquote, because it's got to drag the other rowers with it.
So that's a scattering angle of 180 degrees, and then the resulting difference in momentum would then be imparted on the electron, which then will fly in this direction with a final velocity. So we know that momentum is conserved, and at the quantum mechanics state, energy should be conserved as well. And
so there's no proof of this. So he doesn't show us the experiment where any of this could possibly even be measured. The only they measure this is the net effect. So they send 1 billion photons in and see what they get out in terms of energy out in different directions. Where photons get scattered, they can measure that, and they can measure voltage, but they can't measure anything else. There's no way to test this theorem.
Since the reflected photon will have a longer wavelength, therefore it will have lost some energy. That energy would then have been imparted on the electron, so we should be able to see that the change in momentum will be given to the electron, and the change in energy will be given to the electron. In each case, the final velocity calculated with each of those interactions should be the same. All right, let's find out if it is. So first of all, what we want...
So I'll show you this, but I don't even know if there's any point in really going through it. He just goes through circular mathematics. So he solves the equation going this way, and then he solves the same equation just going backwards the other way and says, look, that come up with the same answer. Yes, you just did the same equation backwards. Of course you come up with the same answer.
What we want to do is we want to go ahead and see how the wavelength changed in this case. And so we can say that lambda prime minus lambda initial, and of course that should be a subknot right here, lambda initial is equal to h over mc times 1 minus the cosine. Of course the cosine in this case is going to be 180 degrees. And plugging the numbers, this comes out to be 6.626 times 10 to the minus 34 divided by 9.11 times 10 to the minus 31. Of course that's the mass of a electron in terms of kilograms, and then c would be 3 times 10 to the 8. And then, of course, the cosine of 180 is minus 1. Minus times the minus 1 is 1. So 1 plus 1 is 2. So we multiply this times 2. And that will give us the change in the wavelength.
All right. So that's what I just wanted you to see, is this 2. Okay? Because I can explain that 2. They really can't. They can't explain why the 2 is necessary. Why am I doubling the effect? Oh, you're doubling the effect because it's really an exchange of energy. It's not a reflection. The reflection, the photon doesn't scatter off the electron and then the electron go its way and nothing else ever happens. No, that doesn't the way it works. The way it works is the photon is absorbed by the electron gives back the opposite in the case of reverse reflection. And now the electron moves much slower through space, and then it re-emits the photon some time later with less energy, depending on which way it releases it. Obviously, if the electron's moving this way and it releases a photon that way, the frequency is going to be slower, right? So, this one, even the relativists should admit that it's a truth. Okay, that if you're releasing a photon as quanta, okay, as bits of that wave. If you do quantum mechanics, if you understand the idea of quantized energy, Yes, I'm being sarcastic. Okay, if you quantum whores can get it, that it's in quanta. Okay, that's the photon is made out of bits of energy, lumps of energy, whatever you want to call them, wavelengths of energy. Then you can understand that if the electron is moving this way, and it's going to give back to the universe energy in a direction, that it's going to give it back at a rate at which it's going to slow down, which depends on the speed of the random force, okay, that it's moving into. It's going to hit more force going with it than against it. And the point is it's giving back something inside of it, and it's going to give it back at a rate that's going to be commensurate to the direction it's moving. So if you were throwing a baseball and you're moving this way, right, and you're going to throw the baseball this way, your baseball leaves faster because it gets to combine both motions. Now, if you throw the baseball out the back of the train, so to speak, okay, then the baseball is going to be moving much slower. It might not be moving at all. I mean, it might have no motion. You're throwing it 90 miles an hour. The train's moving 90 miles an hour. It's not even going to get out. But let's not play with that. Let's say it gets out. So the point is that obviously from the back of the train, if you're going to release a baseball, the baseball is going to have a wider distance between the release points, because this distance is always gaining on you. You're changing your position each time you throw the ball. You're changing where you are. And so when you throw it from here, that's one clump. Then you move and then throw another one. So that's going to be this clump. It's going to be this distance is going to be this distance has to be added to this distance between when the baseballs are in the order they're in. So the frequency gets wider, the wavelength gets longer for the reflected stuff, the stuff going backwards, and the wavelength gets tighter for the stuff forward because you keep gaining on it. When you throw one baseball, you move forward to throw the next one, and so now their order will be much tighter. So, this one will be a tighter frequency, this will be a wider frequency. Even though you're throwing exactly the same, it depends on which way you're throwing it. And that's what the electron is essentially doing, is it's throwing from its momentum, and that's what changes the frequency. It doesn't change the speed, because they all go the same, the light speed. So it's just releasing birds, and it's releasing them from different positions. In this direction, it's releasing birds going this way in this direction, so that means the birds end up closer to each other. And when it releases the birds going the backward directions, the birds, even though I released them at exactly the same time, they end up further apart from each other because I'm moving away from the direction I'm letting the birds go. That should have been understandable. And that's why the frequency changes. So I can explain the experimental results, why there's a frequency change, okay? And you don't need this, whatever this is, mathematics.
Of our photon. So we get 6.626 e to the 34 minus divided by 9.11 e to the 31 minus and divided by 3 e to the 8 and then multiply times 2, and that would be the change in the wavelength of 4.85 times 10 to the minus 12 meters. All right, so now we have to imagine what would be the wavelength.
So let's understand, it's a tiny, tiny, tiny picometer change. So this isn't even relevant to visible light because the motion of the electron is so not fast that it can't change the frequency of regular light by very much. Can't make it much closer or much further because the train's going 1 mile an hour and the birds are flying 500 miles an hour. So you can't make much of a change with your moving train. And so the only one you can make a change to is ones that are moving very fast, that they're already starting off moving very fast, very high frequency. Then you can make an effect that you might be able to notice. But you can't make an effect you can notice with anything that doesn't have an extremely high frame rate, so to speak.
Of the incoming photon. Let's say that in this case, we're going to make that into 100 picometers, which is equal to 0.1 nanometers which is equal to 100 times 10 to the minus.
So in his other video, he did actually make a mistake because he said it was nanometers, 10 nanometers or whatever, and that was, that would be a pretty lame X-ray, where, 0.01 picometers that's a really small frequency. So that's a very high energy, okay? And it's only high energy because it knocks you over really fast. There's no rebounding at all. You don't get to rebound at all when something's hitting you with that kind of frequency. You don't get any time to readjust your position before the next thing hits you. So you're going to be just bowled over, so to speak.
12 meters. So let's say that's a pretty energetic photon. That would be a photon of an X-ray. And so let's say there's an X-ray photon impacting the electron. What will be the change in the momentum in this case? So momentum initially is going to be h times the wavelength initially. And so we have an initial wavelength of 100 picometers. This becomes 6.626.
So this is where he's just already said this is the information we're putting into the formula. And then he'll later say, look, I confirmed it. But he'll confirm it because he already put it in.
Times 10 to the minus 34 divided by 100 times 10 to the minus 12. And just to make sure I get this right, 6.626 e to the 34 minus divided by 100 e to the 12 minus, and that would be 6.626 times 10 to the minus 24. And of course, the momentum would be kilograms meters per second. So those are the units of momentum. The final momentum.
Right, so that doesn't mean anything, right? Because you didn't put it into electron volts or something else that you could make a comparison with. So it kind of just doesn't mean anything in a number, except the fact that you can know it's a small number. But that's all you get. So let's just jump ahead. It's like I said, it's just formula
6 e to
after
the 34
formula.
minus divided by 104.85 e to the 12 minus equals, and so the momentum of the scattered photon is going to be 6.320 times 10 to the minus 24 kilograms meters per second. So that gives us a change in momentum. So the change in
Right, so it's 24 and 24, and the change is 0.3 of something to the negative 24th. So it's obviously an insanely small change in the momentum, the frequency. Again, they'll convert momentum. That is how. See, this is the problem. They sort of say it's kilograms per second per meter. Is just a very strange quantity.
momentum. Now also we have to be careful, because in one case the momentum is to the right, that's a positive momentum. Here it's a momentum to the left, which is negative momentum. So the difference in momentum is basically the sum of the two, because we're subtracting a negative momentum on the way back. So that means that the change.
So momentum. So this is another thing where they're playing a game, because there is no difference in the momentum dimensionally. You don't count speed and multiply it. So if I'm going 70 miles an hour this way and I switch and go 70 miles an hour this way, it doesn't mean that I'm going 140 miles an hour this way. You don't consider what I was doing. You consider what I'm doing, period. So essentially he's doubling the speed, the momentum, through the reflection. He's saying that the reflecting object essentially is going twice as fast because it's converted from going in one direction to the opposite direction. That means it's going 140 miles an hour compared to its original velocity. It's obviously not going 140 miles an hour. You obviously don't make a comparison to its original direction and say its momentum has doubled. Its momentum didn't double. So, I mean, this is just, this is just garbage. This is where math can just make a mess. And he's just making a mess. He just doubled its momentum. Plainly. 70 miles an hour is 70 miles an hour. It doesn't matter what direction it is. That's the momentum. You can't make the 70 miles an hour 140 miles an hour by saying, well, I'm going to compare it to where it was going. It doesn't matter where it was going. It doesn't matter where it comes from. Conservation of momentum means conservation of its speed, not its direction.
Momentum, the delta P, is equal to P initial minus P final. But remember, that is a negative quantity, so this is equal to 6.626 times 10 to the minus 24.
The electron is the thing that has to do the throwing, right? So if an object hits another object, right, you have this idea that all the energy in this goes into this and this moves. So that's kinetic. Kinetic balls, Newton's cradle, right? All the energy in this just goes into this stops. So the argument is it's not going to stop. So that means something has to throw it back. So they're making an argument that the extra throwing out of it back is happening in the photon's energy, rather than recognizing, no, that's energy that the electron has to provide. If it's going to throw it back, that means this has to rebound and throw it back somehow. It can't just magically happen. So this has to be elastic. This has to be inelastic in the sense that the object has to be able to go in and be pushed back out, and this thing stays where it is. You can't have it both ways. You can't have this move and this reflect unless you understand there's an exchange being made. There has to be some component that goes this way that somehow is a free exchange with something. You exchange something. You can't make it work kinetically. You can't make this go this way and this go the opposite direction. This has the same momentum it had going in, almost the same, and this gets to move this way. That can't happen.
Minus 6.320 times 10 to the minus 24. So the change in the momentum of the photons is going to be, so we have this number, and we're going to add to that plus 6.626 e to the 24 minus, and so we get a change of 1.295 times 10 to the minus 23 kilograms meters per second. So that would be the momentum given to the electron. So how fast will the electron move away from there with that kind of change in momentum? Remember that initially the electron has no momentum at all. It just stood there, well, hypothetically of course. And so now it gets hit by the photon. The electron will then get pushed away. And so the loss in momentum, because this is really the loss of momentum of the photon, will then be the gain of momentum for the electron. So therefore, since the momentum
So again, and all they're doing is turning this again into frequency. Frequency is a definition of its momentum. When, no, its momentum is defined by the speed of light.
Of the electron is going to be m times v, because it's the v final of the electron is going to be the p final divided by the mass, and the momentum gained by the electron is the momentum lost by the photon, which would be 1.295 times 10 to the minus 23 divided by the mass, which is 9.11 times 10 to the minus 31. And so we can say that the final velocity is,
and it's going to come out huge because well, no, he's dividing by a 31 into a 23.
Just to make sure I find the correct decimal point. So that's a 6.
Dividing a big number into a little number.
14.2 times 10 to the 6th meters per second. So that's less than 1% of the speed of light, so it's not relativistic, so we can go ahead and...
So it's a huge increase. So he's taking a tiny bit of frequency off and gaining this huge increase in the momentum of the electron. Now, it's not real momentum in the sense it has to be spread over the entire mass of the electron, so that can't even mean anything, because somewhere in there has to be the mass of the electron, which I guess is this 31 number. But again, it's just way too much energy to get out of a change in frequency. And the real effect is the fact that the tipping point of the electron, the one that creates the electricity, the thing we can measure, is frequency dependent, but everything else isn't. Anyway, there's no point in going through all this. Anyway, so I just prove it's just all math going all the way down, and so everything ends up just recalculating the same equation in reverse and coming up with these two numbers that are the same. And he just did the same thing over again in just reverse order. So there's nothing there, really. It's not a proof of anything. And again, there's no experimental results anywhere here for anyone to analyze to say, yes, that's what actually physically happened. Because it's not what physically happened. This is not actual physics. This is mathematics. And it's premised wrong. And not likely to be entirely correct. And I'd say these energy numbers are wrong, because they're defining energy based on being able to change the frequency of something and change its energy, when changing its frequency doesn't change how many quanta, how many bits of energy it has, is not changed by changing its frequency. And they're assuming that as I make this thing smaller, closer together, I'm adding more quanta. And they're not adding more. They have to work with the ray length that they started with, and any change is still the same number of bits. Alright, that's probably enough. We'll call it enough. So, till the later. So I'll probably be trying an experimental video later today. You know, a live room, blah, blah, blah. See how that goes. Conversational thingy, whatever. See what happens. So, might work, might not. Take it for whatever it'll be. We'll see what it'll be. I haven't done one in a while. Who knows? YouTube might have broken the thing. Who knows? I'll find out. You might find out. Or not. So, till then, and such. Or not.